Hello there. This is my submission for the Fluent project number 2 for the summer of 2025 Fluid Mechanics class. I'll be working with my partner Jesse Chotner on this project. So we can go ahead and get started. I'm first going to pull in a Fluent analysis system from the toolbox and place it in the project schematic. Start by opening up our geometry, and we can create a new design model over geometry. Give that a moment to load. Now that the design model is opened, I'm going to click on our z-axis so we can get a 2D view of our sketch. Go over to sketching, and we create actually before we create a rectangle, I'm going to change our units to centimeters because that's our what we want for our analysis. And I'm going to now create our rectangle. I'm going to start a rectangle at the origin, drag it out, and now we have an arbitrarily sized rectangle. Now we're going to want to dimension that rectangle. We can use our general dimensions, selecting our top side of the rectangle and our front side. And then we can change the length, which we want to be 100 centimeters, and our height is going to be 10 centimeters. Now that we have our properly dimensioned rectangle, we can go ahead and actually create a surface for that. And this is going to be in concept, surface from sketches. I'm just going to change our selection option to box select so I can select all these lines at the same time. And then we can go ahead and select generate. Now you can see that our surface has been selected or created. We can go back to workbench, verify that our geometry is okay, and then start with the meshing process. So I'm going to double click on mesh and open up that window. Okay, so our geometry we just created is loaded into the meshing software. There's a few different things you can start with, but I'm going to start with creating our name selections. So I'm going to start with I changed our select mode to edge select. I'm going to select our top edge, go down to create name selection, and we're going to name this far field. And then we can go to our bottom side, same process, we're going to name this plate. And then our front side of our rectangle, we're going to name the inlet. And the back side, we can name outlet. Oop. Change that. And then I'm just going to create a face selection, change our selection mode to face. And then the same thing, create name selection. And then I'm going to use airfield. You can see our name selections have populated in the toolbar, so we can go forward and create our mesh. I'm going to start by creating a face mesh, just to get us started off. Select our face, apply, and then all these basic options can remain the same, and then select generate. Now that our face mesh has been created, so we have a very basic mesh. We're going to refine our mesh a little bit more. I'm going to create a sizing mesh. So we can start with, let's go back and change this to edge. We can start with our top and bottom edges. Click those and select apply. We're going to change our type to number of divisions. And we're going to do 3,000. What's that come out to? You're going to want around 200,000 divisions to get a good mesh. So if we do the math, just going to figure out how high we want it. If we do 3,000, 200,000 divided by 3,000. Alright, we can do 3,000 divisions this way. Start with that. Capture curvature, I want to change to no. And then behavior, I want it to be hard. And then we can select generate. This should take a little bit of time. Oh, it actually did it pretty quickly. Now you can see we have our mesh good and well done this way. And then it's kind of hard to see, but we want to create another sizing mesh on our left and right sides to get a little bit more definition. So we can start with the left side, click the left side, select apply. Same options as before, number of divisions, leave that as so. And then doing the math, you're going to want around 200,000 total divisions. So we can do 200,000 divided by 3,000 that we did along the x-axis. That's going to leave us with roughly 66 divisions. So I'll just go with 70. Keep it a nice number. And same as before, capture curvature goes to no, and behavior goes to hard. But just for the sake of how we're going to want to approach this model and how we want to approach our solution, most of the boundary layer development for this analysis is going to occur right around the bottom side of our rectangle, right around the plate that we named our name selection. So we're going to want to create a bias for this, which we can start as here, which will essentially just move more of our cells towards the bottom, so we get more defined kind of boundary layer development. And then we can name our bias factor 70. Works pretty well. Leave that as is. What if we make it 80? How's that look? Nah, 70 is fine. And then all these other stuff is good, so we can select generate, wait for that to generate. Okay, so now that is done, we can zoom in here, take a look at the mesh it created, and you can see a lot of these cells are really closely grouped together at the bottom. But it's kind of hard to see, but it kind of phases out halfway through. We want to continue that on this side as well. So we're going to create another sizing mesh and select this side this time, right side. We can apply that. Same thing, number of divisions. We're going to do 70 divisions like we did on the left side, just to maintain some consistency. And then the same options, no for capture curvature and behavior turn to hard. We're going to want that same bias, so we can create a bias like so. And then our bias factor will be 70. But you see here that it's actually flipped. So it's a lot more defined at the top instead of the bottom. So we're going to reverse our bias by selecting reverse bias, and then selecting our right side again and selecting apply. Now you can see it flips our bias. And then we can select generate, wait for that to apply. Okay, so now that our mesh is done, let me just take a look, make sure it all populated correctly, which it did. Now we are ready to move on to our next step. So we can go back to the workbench. We're going to update this. Give that a second to load. Okay, so now that it's loaded, we can open up the setup window just by double-clicking the box. As I was saying, leave all of these as is, and then we can click Start to open up our setup options. Give this a chance to load. Okay, so our mesh successfully uploaded into the Fluent solver. Let's see here. So we're going to start by just changing our model. We want laminar flow, so we're going to change our model to laminar. And it's also going to be steady. And these should all be okay. Viscous laminar 2D steady flow. Yeah. So we can just check our mesh just to make sure. Yeah, checks for anything, maybe abnormalities or anything wrong with our mesh, which comes back. Nothing came back as an issue. So next, we can go ahead and define some of our parameters for our material. So we want our material density to be 1.2 kilograms per meter cubed, and our viscosity to be 1.8 times 10 to the negative 5 kilograms meters per second, or per meter seconds. Which is going to be 0.123418. Should give us 1, 2, 3, 4, 5. Yep. And we're going to click change and create and close that down. Next, we're just going to want to make sure this is selected as air. So we're using the right thing, which we are. And we can close that down. And then for our boundary conditions, this is where it gets a little important. Our inlet, we want an inlet velocity, a inlet or free stream velocity of 2 meters per second. So we're going to change this value to 2. Select apply. And then this is all good. Our outlet, not much we have to change for the outlet. Just want to make sure that we don't have any reverse flow. So we're going to check mark that prevent reverse flow. Apply. And then the only thing we're going to want to change for our boundary conditions is what our far field is that we named. Our name selection for far field. What that type is. So right now it's typed as wall. We don't want it to be a wall. It's going to be point of symmetry because we're only modeling half of our plate. So we want this top section to be our symmetry line. So we can go down to, once we have far field selected, we can go down to type, and we're going to select symmetry and just apply that. So that's all good. Our inlet velocity is good. Velocity inlet. That's the interior. Plate is a wall, and our outlet is a pressure outlet. And we can just make sure it's reflected in here, which it is. So next, we don't need to do anything under reference values. The only things we're going to change are some of this stuff. Let me just verify I have this correct. So we have a coupled scheme. These squares based second order, upwind, and global time. It's all good. The controls should be fine, which they are. I think the only thing we're going to change are our monitors. So we're going to change some of our residual criteria. Just so we're going to want to change our absolute criteria to -6, which to give us a little bit more detailed solution. So we can add a couple zeros to that. Should be what, 1, 2, 3, 4, 5 zeros. Yeah, 5 zeros. So we're going to want to change our x, all of this to the same thing. So now that is done, select OK. And then we're going to want to initialize. We're going to do standard initialization. And we're going to select inlet for our compute from location. And we can select initialize. Yeah, let's just do this again, just to make sure. Okay. So now it's initialized, we can run our calculation. Go down to run. And we're going to do, say, 500 iterations. Should be enough. We're going to calculate. So we're going to let this do its thing. let it run out. And we'll come back and view our mesh, not our mesh, our what Ansys has spit out, our results when this is done. Alright, our calculation is completed. Let me take a look at our scaled residuals. See, we got some pretty good convergence. No sawtoothing, which is okay. So we're going to go ahead and go back to Workbench and load up our results. Double click results. Give that a moment to load. I'm going to go back to our 2D view. Then we're going to want a few different locations that we're going to want to analyze. So we go ahead and start at our line. We're going to add a line right around the 35 centimeter mark. Can I not put numbers in there? I guess not. So we're just going to name that line 1 for simplicity. So our object is 100 centimeters long. We want it at 35, so we're going to put it at 0.35. That's 35, and 0.35. This one is wrong. I forgot the decimal. And it's 10 centimeters tall. So we're going to do 0.1, like so. And then we're going to do 100 samples. So there we go. We got our first line in. And we're going to do a second line. Line 2. This line is going to be at 75 centimeters. So same idea, 0.75, 0.75, and 0.1. 1 for the height. 100 samples again. And there's our second line, slightly farther down. So now that we have that in, we can go ahead and create our contour. Contour 1 is fine. And then we're going to want symmetry 1 for our locations. We want it to be our velocity contour. So we make that velocity U. And then we're going to do 110 contours. And click apply. Okay, so there we have it. There is our kind of velocity contour for the flow over the flat plate. Just so we can see this a little bit better, I'm going to move our legend out of the way, move that to the top. And then we're going to go ahead and take just a little look at this just to make sure it looks okay. Which it does. It's looking pretty good. Alright. We're going to do a vector contour as well. So I'm going to just deselect this so we can see our shape again. And we're going to do vector contour. A location. We're going to do symmetry 1. Leave it as vertex. Variable, we want it to be velocity. And we can select apply. So now we can zoom in. Take a look. Really far in. I'm going to go ahead and redo our vector 1. So I'm just going to uncheck that. Going to go back to vector. Vector 2. Our location. We're going to do it over symmetry. We want it to be. I'm going to do equally spaced. I'm because we don't really want it at each vertex. Because we got a lot of vertexes. So if it's 100 centimeters long, let's just say we want, I don't know, two or three. So we can do 300 number of points, and then velocity and apply. That is too little. I'm gonna bump this up to 3,000. Start to get a better look at what's going on here. Maybe we change this back to vertex and select apply. That'll give us a better look. It's still a little hard to see because of the amount of I guess points we have from our mesh. But you know, that is the velocity, vectors. A little hard to see, but it'll do the job. Oh, you can kind of see it on the end. It looks a little better. Yeah, like so. Zoom out. I'm gonna go ahead and delete these because we're not gonna need them. Just make sure our contour looks good, which it does. But we also want our pressure contour, so we can create another contour. Should I go to contour? Just name this pressure. We'll name it P contour because it didn't like that name. P contour. Location is going to be symmetry. We want pressure, and we'll do 110 and apply. All right, we're going to remove this so we can see our pressure. And this is our pressure contour. You can see it's pretty sparse. Not a lot of pressure, except for right at this corner here, where we get, like 1.5 pascals of pressure right at the corner. But other than that, this looks pretty good. Our pressure drops as we go because it's a favorable pressure system. So high pressure on this side, low pressure on this side creates our flow, creates our velocity. So that looks pretty good. Next, we're going to want to create our plots. So we can take a look at each of our lines that we created earlier. I'm just going to remove this, go back to our velocity. This looks a little nicer. So we're going to go up to top bar and select chart. I'm going to name this chart. Velocity chart. Okay. Alright. Velocity contour, we can name it. Okay, so that's what we're looking for. Or delete the profile. Name it profile. Alright, so our data series, we're gonna want two data series here. We're gonna want our 35 centimeter line. Be line 1. Create another series. And our 75 centimeter line should be at line 2. And then we can make sure that our x-axes are right. We want our x-axis to be velocity u, and then the y-axis is going to be the vertical y distance. And we can select apply. Okay, so these are our velocity profiles. at our different lines. Um, our red line is our 35 centimeter line, and our blue line is our 75 centimeter line. What else do we need? For our next charts, we're not going to do it in post, we're going to want to do it in Fluent itself. So we're going to go back to the Fluent window. We're going to go down to plots, and we can select the XY plot. All this is fine. We're going to change our Y-axis just to wall flexes, and then change this to skin friction coefficient. We want this along the plate. We're going to name this skin friction. It's not acyl friction. Coef. And we're going to save and plot. I can close this down. And here's our skin friction coefficient with the position. I'm going to do the same thing for our wall shear stresses. I'm starting to go back to XY plot, double click, select wall flexes, and we're going to do wall shear stress on the plate. And we can name this wall shear stress. And save and plot this as well. We can close that down. And this is what we're looking at for our wall shear stresses. Report definitions is what we want. We're going to create a new force report, and we want our drag. We can name this drag coef. We want to print to console as well. Oh, there you go. So I had to select it. And select OK. So now we have this all set up, and we can close that down. We're going to want to compute this now. So we can go click it back open, drag coef, what we did before, and select compute. Right, cancel. And here is our drag coefficient as computed by Ansys. So we have 0.0176 approximately for the drag coefficient of the plate. Just do one last check. Yeah, and that is all. So thank you very much for watching. Our video kind of just went over how to use Ansys Fluent to solve for the flow over a plate, 2D viscous laminar flow, steady flow as well. And we got our velocity contour as well as our pressure contour. And then the charts for our velocity profile at the different locations, as well as our plots for wall shear and skin friction, and the drag coefficient, which we had a Fluent solve for. So, thank you for watching.